begin. So today I'll try and start discussing loop amplitudes. Okay. Of course, set up the general formalism of how to derive Feynman rules. But we'll see that there is some special features of the loop amplitudes which have to be understood before we can actually evaluate it. And the special feature that you have to understand is the following. So as you saw, if you have a loop diagram, typically you are left with a momentum integration. Okay, because some of the momentum, loop momentum, are not fixed by delta function, the momentum conservation laws. And what can happen is that those momentum integrals can become divergent. So take, for example, a graph like this, okay, in phi-4 theory. Where say we have P1, P2, P3, P4, and we have an undetermined momentum L. Okay, once this is L, then this is of course fixed to be minus P1 minus P2 minus L. Okay, because here it's like P1 plus P2 coming out of this. Okay, so total momentum coming out should be minus P1 minus P2, and I have just divided it into L and minus P1 minus P2 minus L. So this one is proportional to an integral of the following form. We have P4L over 2 pi to the 4, 1 over L square plus M square minus I epsilon, and P1 plus P2 plus L square plus M square. Okay, I have ignored minus signs and i's, etc., which are all outside. So this has potentially different kinds of divergences. One possible source of divergence is when the denominator vanishes. Those are of course controlled by this I epsilon. As long as epsilon is non-zero, the denominator never vanishes because you are taking the integral on the real axis. But you have to worry about whether they eventually remain finite when you take the epsilon goes to zero limit. And in special cases, one finds that they can become divergent when the epsilon goes to zero limit. But those are not the kinds of divergences we will worry about. So the divergences of denominators, these can lead to singularities. But typically the reason that you don't worry about this is because these singularities turn out to be have physical origin. It never happens that, well, I will not say it never happens. If there are no massless particles, then it never happens that these are actually infinite. But what can happen is that the integral becomes infinite, and then you have to worry about whether the integral can be finite. And when there are no massless particles, one can show that the integral never becomes infinite. Okay, the integral always remains finite. So these can give rise to singularities of the amplitudes, but they are integral singularities. But these are not what we will worry about right now. Our worry will be what happens for large L. So we will worry about divergences for large L. Large L means large loop momentum. So these are called ultraviolet divergences. Ultraviolet. Yeah, ultraviolet are in short UV. So in this example, if we take L to be large, then in the large L limit you can ignore these m square factors, you can ignore the p1 plus p2 factors. So this integral for large L goes as integral d4L over L square whole square. Okay, because I just replace this by L square and this also by L square because L is larger than these are fixed momentum, extra momentum. And this is logarithmically divergent. Okay, to see this, what we can do is that we can, here L square of course is minus L0 square plus L square. But we will make a Euclidean rotation. Okay, we will write L0 as I times say L4 and write this as integral d4L over L1 square plus up to L4 square whole square. Okay, it is to estimate whether it is divergent or not. And now what we can do is that we can change variables. We define R as square root of L1 square plus L2 square plus L3 square plus L4 square. Okay, this is the analog of the radial distance but in 4 dimensions. Okay, now all of these dimensions are space dimensions because I have made this change. L0 goes to I times L4. So in this case, see this is a form in which the integral would have arisen anyway if you had started from this Euclidean formalism, right? I gave the path integral. One to define the path integral as I described was to define it fully in the Euclidean space, right? If you had defined it fully in the Euclidean space, then the momentum would have been Euclidean anyway. Okay, and then we got this form by weak rotation. Okay, so now we are saying let's go back to the original Euclidean formulation, in which case the integrals are like this. So if you make this change of variables, then this integral goes as integral r to the power d minus r cube dr omega 3 over r square whole square. What is omega 3? This is the volume of 3 sphere, volume of unit 3 sphere. Is this familiar? Right? The volume element, right, if you go to the polar coordinates, can be thought of as this r cube dr. Okay, this is the generalization of what we are already familiar with in 2 and 3 dimensions. Right? Suppose you have a 2-dimensional integral dx dy. Right? That can be written as integral dr times 2 pi, right? Because 2 pi is the length of the unit circle. Right? In 3 dimensions, okay, integral dx dy dz, I can write as r square dr times the volume of the 2-dimensional sphere, which is 4 pi. That's 4 pi r square dr. This is the generalization of that in 1 higher dimension. Okay, and in fact, omega 3, there is a formula for omega 3. This is 2 pi square. Okay, a 3-dimensional sphere has area, unit 3-dimensional sphere has area 2 pi square. Okay, if you have not done this before, I will leave it as an exercise to do this. And you can take a 3-dimensional sphere, take x, y, z, w, write a surface x square plus y square plus z square plus w square equal to 1 and try to calculate its volume. And you will find that this is 2 pi square. Okay, the details are not important, but what is important is that if you look at the power of r, we have r cube and r to the 4. So this goes as integral dr over r. And of course, you shouldn't trust it for small r, right? Because for small r there are various corrections which I have ignored. But you will see that for large r, it goes as dr over r, okay, and hence its logarithmical divergent. Right? If you take the upper limit to be lambda, this goes as log lambda, and that goes to infinity when lambda goes to infinity. to take this to be a lambda, this goes as log lambda, and this goes to infinity as lambda goes to infinity. Is this point clear? Okay. So you see that this integral is logarithmically divergent. Okay. And in this case, you can show that for generic values of the external momentum, this is the only kind of divergence that we encounter. Okay, the divergences that are coming from the zeros of this. Okay, as I said, sometimes you may get divergences from here, but they are not very serious. Typically, they are always integrable divergences. Just to convince you, let me do this once anyway, to show that these divergences are not too problematic. So let's look at where the poles are, the denominator, right? Where the denominator can vanish. And we look at it as a function of L. So this is real L0 and this is imaginary L0. This one has zeros at L0 square minus plus L square plus M square equal to 0, which gives L0 equal to plus minus square root of L square plus M square. Right?
You're not taking the I epsilon.
Okay, let's put the I epsilon minus I epsilon equal to 0 minus I epsilon. So those are here and here. This one has at minus Q1 0 minus P2 0 plus minus square root of Q1 plus P2 plus L square plus M square. So those will be like, say, here and here. Okay, it doesn't matter where, it can be in different places. But typically what can happen, what you can do is that you can deform the contour so as to remain far away from these poles, because contour integral, as long as the endpoints are fixed, you can deform the contour in any way you like. Okay? So you can deform the contour to move these far away from the poles and avoid the poles there. Okay? Sometimes you may get singularities when these poles approach each other, right? Suppose the two poles, the positions of the poles dependent on these variables, right? So sometimes it may happen that the two poles approach each other from opposite side, and you cannot deform the contour away from those poles. Okay, and that's the place where you actually get singularities of these integrals. But those singularities, as I said, can all be integrated, right? The integrand may be singular. It's like integral dx over root x. Right? The integrand is divergent at x equal to 0. But the integral is not divergent, right? It's integrable. So the kind of singularity that you may get possibly from the poles approaching each other, you can show are all integrable. Okay, as long as there are no massless particles. So these are not the poles that we will be worried about, right? Our main worry will be the divergence of this kind. Okay, coming from large values of momentum. Are there questions? Now, I gave you one diagram where these divergences appear, but these are in fact very generic. Okay, there are many diagrams which can give rise to divergences. So let me write another diagram.
Sir, what if we have a continuum of poles?
See, in any finite ordering perturbation theory, you never have continuum of poles, right? You always have a finite number of poles because there are after a finite number of denominators. So you don't encounter a problem of continuum of poles. The divergences come when the poles approach each other. Right? That's where the problem comes from. Yes.
they are approaching each other.
Yes.
You are always managing them off the x-axis where you are actually integrating. So how does it matter?
Well, eventually you have to take the epsilon goes to 0 limit, right? So the question is when the epsilon goes to 0 limit, yes. So you can do the integral keeping the epsilon finite. But the question is, as you take the epsilon goes to 0 limit at the end, do you get infinite answer or finite answer? And what you can show that in 4 dimensions, as long as there are no massless particles, you always get finite answers. If there are massless particles, then sometimes you have divergences, and then you have to worry about how to deal with those. Okay, these are called infrared divergences, but those are not the ones that we are going to bother about right now. Right? Let's assume that all particles are massive for now, and proceed.
This feature you said that if there is a massless particle, then
4 and less dimensions.
4 and less.
Yes. You can see that the ultraviolet divergences become worse as you go to higher end dimension, right? Because this part starts increasing. Whereas the infrared divergences become worse as you go to lower dimension, because this part starts decreasing. So the small L region can have a large numerator, and the numerator doesn't go down sufficiently fast to compensate for it. So infrared divergences are problematic in lower dimension, ultraviolet divergences are problematic in higher dimension. In 4 dimensions, you have both kinds in general, and you have to deal with those, but separately. Okay, so now let's look at some other diagram. Okay, again in 5 to the 4th theory. This diagram, is it divergent or not divergent? We are talking about ultraviolet. This will be like, if this is L, right? So P1, P1. This is integral d4L over L square. Right? So if you again change variables, this goes as integral r cube dr omega 3 over r square. Okay, to the upper limit lambda. So this is a clearly divergent, right? Integral r dr. So this goes as lambda square. Is this? Right? But not all loop diagrams are divergent. Okay, one can write down examples of loop diagrams which are convergent, and here is one of them. You take again in 5/4 theory. Okay, if you have a diagram like this, suppose this is L, this will be L plus something, and this will be L plus something, right? The something is whatever momentum is entering from here. But if you look at the large L limit, then this goes as d4L over L square cube. Right? Because this is giving an L square in the numerator, this is giving an L square, this is giving an L square. So this is finite, right? Because this will go as integral r cube dr omega 3 over r square whole square, r square cube. So this goes as like dr over r cube. Right? This is r cube versus r to the 6. So this goes as dr over r cube. So this is finite, right? There is no divergence from the upper end. Is this clear? See, lower end you shouldn't worry about, because this is the fact that it's r cube, we have already made an approximation that r is large. Okay, because lower end there are various momentum factors, mass factors which will cut off the lower end. So this is not divergent. So this is divergent. This is finite. This is divergent. And you can discuss this also for higher loop amplitudes. Okay, there are similarly finite diagrams and divergent diagrams. So the renormalization is the program that tries to make sense of these divergences. Right? Even though there are divergences, if you are going to use quantum field theory for physical amplitudes, you have to know how to get finite answers from these divergent diagrams. And this program is what we normally call renormalization. Okay, that how can we make sense of these divergences? So renormalization and so this program has two main steps. The first step is to introduce what is called a regularization. Regularization. To make this makes each diagram finite. By some kind of cutoff. The simplest cutoff that you have is to take each momentum and put the upper limit of the momentum integral not from minus infinity to infinity but from minus lambda to lambda. Okay. Then of course everything is finite. So take simplest possibility. Take L mu between lambda and minus lambda for all momentum. Now this is not a very systematic cutoff because it has many problems. Right? It has problems that first of all it's not Lorentz invariant. If you take L mu and make a Lorentz transformation, then the cutoff changes. Right? So this is not Lorentz invariant. This depends on how you label the loop momentum. Right? For example, here I took this momentum to be L, this is L plus something, this is L plus something. Right? I could have taken this to be L, right? This to be L plus something, this to be L plus something, right? Putting the restriction on this momentum, that kind of restriction, and putting the restriction on this momentum gives different results. Is that clear? Because effectively, suppose this is one way of labeling, right? But I could have also labeled it like this. This is L. Okay, so let's maybe write some momentum. So this is P1, P2, P3, P4, P5, P6. Okay? P1, P2, P3, P4, P5, P6. So if you call this L, then this becomes L minus P3 minus P4. And this becomes L plus P1 plus P2. Okay, these are all going out. But the same diagram, suppose you call this momentum L, then this becomes L plus P5 plus P6. And this becomes L minus P3 minus P4. Same diagram, it is referred to as leveling. So if you say that you will restrict each component of L mu between minus lambda and lambda, that restrictions gives you certain restriction on the loop momentum here. But if you use this L and put the same restriction, that's a different restriction here, right? Because this L is related to this L by L minus P3 minus P4 here being the L here. Right? So if you restrict this L to go from minus lambda to lambda, this L effectively goes from in some other range. Right? So it's not even invariant. So this kind of cutoff is not even invariant under releveling of the loop moment. Okay? But I just gave you an example. Okay, there are other more sophisticated versions of the cutoffs which we'll be discussing later. Okay? But the first step is to make it finite somehow, okay, by putting a cutoff. Okay? Result may depend on how you have cut it off. Okay? Final result will certainly diverge if you take lambda goes to infinity. Right? If this is the only thing that you do. But you do something to make it finite first, okay? Because if you don't make it finite, then you cannot really proceed, right? Because you cannot manipulate infinite quantities, right? You have to have some way to make things finite. Okay, are there any questions? So as I said, these are very crude versions of regularization. We will discuss a more sophisticated version of regularization. But the basic idea is that we introduce some parameter such that as long as that parameter is kept finite, the results are finite. Eventually, you want to take the parameter to infinity, okay, which is analog of the lambda, okay, because you really don't want to put a cutoff at the end. So say step 2, which is the non-trivial part. This can be stated in many different ways. Okay, so I'll do it in 2 different ways now, and then later on we will see even a third way. So suppose we have made this finite. We have expressed all S matrix elements, which are the physical quantities, in terms of the various parameters of the theory. Okay? So these relations, S matrix as a function of the parameters, if we now keep the parameters fixed and take the cutoff to infinity, the S matrices will become infinite. Because after all, the initial S matrix are divergence, right? So if you take the cutoff to infinity, S matrix will become infinite. But now we use the fact that the parameters of the theory, okay, that we have introduced, okay, they are not directly measurable. Okay, we want to find something that is testable. Right? We want to find some testable predictions of the theory which you can measure in experiment. Okay. S matrix is something you can measure. Okay, or more precisely, the mod square of the S matrix is something you can measure. But the parameters m and lambda, which are in the 5-4 theory, those you cannot measure. Right? We can measure them if we can relate somehow m to the mass of the particle. Right? But mass of the particle is coming from the poles of the 2-part function, right? Let's suppose that we don't know the relationship between them and the poles. So parameters are not physical. So what we can try to do is to detect many different S matrix elements, which may also contain 2-part function, and then we eliminate those parameters which are only a finite in number, right? M and lambda for 5-4 here. So we eliminate those parameters and find relationship between different S matrix elements. Is this clear? So the S matrix elements, S matrix are functions of parameters. M lambda. So we eliminate M lambda and write down relation between S matrix elements. Maybe I can just say, instead of S matrix element, observables. So the physical mass of the particle is also an observable.
Relation between the observers will some sort of difference or ratio like that.
Well, it may be more complicated. Okay. So you eliminate. So take 2 particular observables, which are given in terms of m and lambda. Use those to write m and lambda in terms of the observables. This you can do because everything is being done at finite lambda, like cutoff you have kept finite. So observable m and lambda can be expressed in terms of the observables. Now take a third observable, which you know in terms of m and lambda, but m and lambda has been expressed in terms of two other observables. So express the third observable in terms of these two observables. Is that point clear? Now m and lambda are not theoretical. Okay, it's a relationship that tells us one observable in terms of two others. All calculated from this theory, right? Except that the original parameters m and lambda are not there in the final relation that we are using. Now there is no escape, right? Now everything is an observable, right? So now we can ask, is this relation, okay, observable A given as a function of observable B and observable C? Now you take lambda goes to infinity, take the cutoff to infinity in this relation. You can ask, is this generating a finite relation? Does this relation remain finite as lambda goes to infinity? Is this clear? Okay. We are not asking if observable C given in terms of m and lambda remain finite as lambda goes to infinity. But we are asking if observable C given as a function of two other observables A and B remain finite as lambda goes to infinity.
So is that true that once we have to take lambda going to infinity, or that relation should be independent of lambda?
Well, yeah, no, you have to take lambda goes to infinity. For finite lambda in general, that relation may not be independent of lambda. Right? There will be correct terms of order 1 over lambda square, right, which will all go to 0 as lambda goes to infinity. And in general, it is not true that the relation will be independent of lambda.
So these observables are like physically physical mass or something?
Yes, one observable could be physical mass. Right? So you calculate the physical mass by looking at the poles in the two-point function as a function of m. It will have the structure that the leading contribution of course will be m, right? But that at one loop it will get some corrections, right? At two loop it will get some corrections. So the physical mass will be given by m plus some corrections, which will be in general divergent as lambda goes to infinity. Right? But you work at finite lambda. Use that to write m in terms of physical mass. Instead of thinking of this physical mass being given as a function of m, you invert that to write m as a function of physical mass. Right? So that will also have the structure that to first leading order m is equal to physical mass, and then there are corrections. Those relations are also divergent. As you take lambda goes to infinity, in general they are divergent. But now you calculate another observable, and similarly you calculate, say, physical 4-point coupling. Okay, that's given as a function of lambda, okay, and m. Okay, the leading contribution to the physical 4-point coupling is just lambda itself, right? Because the tree-level diagram for 4-point scattering is just this one. Okay, so it's equal to lambda. But then at hard loop there are corrections, right? So the physical 4-point coupling is a function of lambda, okay, which begins at lambda, then there are ordered lambda corrections, and so on. The invert is to write lambda as a function of physical 4-point coupling. Now you take a third observable, say 5-point scattering. We know its expression in terms of m and lambda, right? But from explicit Feynman diagram calculation. But we also know what m is in terms of physical mass and lambda and physical coupling, and we also know what lambda is in terms of physical mass and physical coupling. So eliminate m and lambda, okay, and write the, say, this third observable, which is the 5-point scattering, in terms of the physical mass and physical 4-point scattering. Now you can ask, is this relation finite as lambda goes to infinity? This is clear? Okay, this is a question that is different from asking whether the 5-point scattering expressed in terms of m and lambda finite as lambda goes to infinity.
So this coupling lambda and
Yes.
the cutoff lambda, they're
No, they are different. Yeah. So cutoff will make, if that confuses you, let me put capital M. Okay, this is some big vast cutoff. Yeah. So the coupling lambda has nothing to do with this lambda. Okay, it will be what? There will be 2 epsilon. So I guess good that you start getting used to 2 symbols of the same name. Okay. So is this clear?
So what's specifically the limit lambda goes to infinity?
Or m goes to infinity, because ultimately the original theory didn't have the same, right? You are integrating L mu from minus n to infinity. So eventually to get a sensible theory, you have to take the n goes to infinity, right? So the point is that a physical observable, so observable C is equal to some function of observable A, which could be the physical mass, observable B, which could be the physical 4-point coupling from the S matrix, and M. M has appeared because M has all integrals are defined with this cutoff, right? So now we are asking that if you take this function and take M to infinity, does this generate a finite function or not? If this generates a finite function, we call the theory renormalizable. If this function is not finite, as capital M goes to infinity, then the theory is not renormalizable. Okay? So this is a distinction between a renormalizable theory and a non-renormalizable theory. So take M goes to infinity. If F is finite in this limit, then the theory is renormalizable.
So first the third observable is written in terms of the Gantt parameter.
M and lambda, yes, because that's the Feynman diagram calculation will give you the third observable as a function of M and mass and lambda and this capital M, right, which is the cutoff. Okay, again there are two names which are the same, right? M, there is a small m for the mass, right? Mass parameter, and capital M for the cutoff. Okay, so whatever it is, this is distinct, right? This is just a cutoff parameter. So now we eliminate the mass parameter and the coupling parameter in terms of physical observables, which are observables A and B, right? Which could be the physical masses and physical 4-point coupling, but it could be anything else. Take any two observables and write a relation like this. And now you take the cutoff to infinity. Okay, and ask if this is a finite function. Yes.
See, this observable C as,
Yes.
as M goes to infinity, and we need to find that what happens for A and B and
See, you don't ask what happens for A and B, because once you have eliminated A and B are now independent parameters. You see, A and B are functions of the mass parameter and lambda, right? We have now expressed the mass parameter and lambda in terms of A and B, right? So now A and B are our arbitrary parameters, right? These are measured in experiment. Okay, so experiments of course don't care about any cutoff, right? Experiments give you the value of A and B, okay, which of course have to be finite because experiments don't measure infinite quantities, right? So you measure them experimentally. Those are your parameters in terms of which you are trying to express everything. Theory gives you the observable C as a function of observable A and observable B. Okay? As far as the theory is concerned, these are independent quantities now, right? Because these are given as a functions of small m and small lambda, but those small m and small lambda now have been eliminated in terms of these, right? So instead of thinking of small m and small lambda as independent quantities, we think of these as independent quantities as far as the theory is concerned. So now when you take capital M to infinity, we keep these fixed. Because these are now our independent parameters, right? We keep these fixed and take capital M to infinity. Okay, because theory is telling us that eventually you have to take capital M to infinity, right? You don't really have a physical cutoff in nature. At the same time, theorists know that these are observables, so these you can actually measure in experiment. So these you think of as independent parameters, right? which the experiments will give you. And now you want to see if this relationship remains finite as capital M goes to infinity.
So are there other observables other than this mass and coupling, this M and lambda?
Well, of course, there are infinite number of observables, right? But you need two to eliminate two parameters. For 5 to the 4th theory, because you have two parameters, m and lambda, small m and small lambda, right? You use two observables, any two, okay, to eliminate small m and small lambda, right? And write every other observable in terms of those two. Is this clear?
This has to be done order by order.
Yes. So this has to be done order by order in Pater-Beauson theory, right? Everything that will be saying, okay, you go up to a given order in Pater-Beauson theory, and then you carry out this procedure. Okay? So when you say that we invert the relationship between small m and small lambda, which are the parameters, and the observables a and b, you do this inversion in a Pater-Beauson expansion. Yes.
Your initial Lagrange did not have this mass scale m as a parameter of the Lagrange.
Capital M, yes.
So any physical observable that you are defining should not be dependent on this. Right?
If the theory is sensible, it shouldn't.
Yes. So I'm saying in that case, this observable field should be precisely independent of m if you have eliminated those other parameters.
No. Because the point is the calculation, you have put this m as a cutoff, right? So you have changed your theory. See, once you have a cutoff, you have changed your theory, right? Only in the m goes to infinity limit you can hope that you will recover a cutoff independent story, right? See, if you are defining your momentum integrals by putting this cutoff, then of course things will depend on m, right? Because you are saying that the loop momentum cannot become larger than m. That's not the theory we started with. Right? We have introduced this cutoff m by hand. Right? So now everything that the theory calculates could depend on small capital M. But the real question is whether you can now take capital M to infinity and recover a sensible capital M independent answer. Right? If the expression contains divergent pieces as capital M goes to infinity, then you don't get a sensible answer, right? So this is the key issue, that whether these relations of this kind that you write have a sensible limit as capital M goes to infinity. The fact that it depends on capital M shouldn't be a surprise at all, because you have introduced capital M as a parameter in the intermediate state analysis, right? So only in the capital M goes to infinity limit you can hope to get an answer that is finite and M independent. Right? If this result, for example, contains a term proportional to log M, log of capital M, then as capital M goes to infinity, it doesn't go to a finite value, right? Then the theory is not renormalizable.
This relation holds, this normalized computation is added up to all order, then you will say the theory is unique.
Up to a given order. You can show that, I mean, as long as it's true to any given order in Pater-Beauson theory, then you will say that theory is renormalizable.
Saying that, can we say that then this UV finite basically is extended up?
Well, it doesn't say anything about whether the sum is UV finite or not. Okay, that's a different issue altogether. So the sum converges or not, that question renormalization doesn't practice. Okay? Renormalization is that you fix a given order in Pater-Beauson theory, it doesn't matter, 100th order in Pater-Beauson theory, and you should be able to prove that to that order in Pater-Beauson theory, you can get a sensible relationship of this kind after you take the M goes to infinity. Now, if you really think about it this way, then it would seem surprising that there is any renormalizable theory at all. And the reason is that there are infinite number of observables. Right? The theory has infinite number of S matrix elements. You can put arbitrary number of external particles, arbitrary momentum that they carry. Right? Continuous family of observables. Right? For generic momentum, generic external particles. And for a theory to be renormalizable, all of these relations, all of these observables, you can express in terms of these two observables, right? And M. All of these functions have to be finite as capital M goes to infinity. Not one function or two functions. Is this point clear? So every function that you have that relates observables, okay, one observable in terms of others, right? In the case of Phi-4 theory, there are two other observables. One observable in terms of two other observables. Okay. Every relation of this kind should have a finite limit as capital M goes to infinity.
So how do you check that?
How? Yeah. So that will check. That's what you have to learn, right? How we check that, right? So how do we prove that theory is renormalizable, right? So we'll see how exactly this is done.
Even though we have infinite number of functions, we have everything determined in terms of observable A and B.
Well, you can change the observable if you
Yeah, I mean,
observable if you want. In terms of two observables, yes,
Everything in terms of
yes, exactly. Okay. Now, I am going to give a slightly different view of renormalization, okay, which is equivalent to what I did here. Okay. And in this different view of, see here, in this way of describing it, okay, I gave some special treatment to these. Okay. We eliminated M and lambda in terms of some two observables, and then I express everything in terms of these two. Okay. I don't want to give any special preference to any particular observable. Okay, so let's see if we can get around that. So again, let's work in the context of Phi-4 theory, but this is general. So I have any observable, let's say A, as some function f, let's call it fa, of m, lambda and capital lambda, capital lambda, which is the cutoff. Right? This is the cutoff. And our problem is that if we keep m and lambda fixed and take capital M to infinity, then this function is divergent. That's the meaning of the original expression being ultraviolet divergent. Okay? And if we keep these parameters fixed, okay, then cutoff cannot be taken to infinity. But now we ask a slightly different question. Again, that relies on the fact that these are not physical quantities. Okay, these are some parameters that you have written in the Lagrangian. Experimentalists don't measure these directly. Right? Experimentalists only measure the S matrix, other observables. So we ask the question: is it possible to find some functions so f1 of x and y and f2, and maybe I shouldn't call it x and y, let's call this a and b, f2 of a and b, such that these are a, b and lambda and m. Okay, this is a bit more abstract than what I described last time, but this has entirely exactly the same content. Okay, so I'll try to explain why this is the case.
That AB are new parameters.
Yes, AB are new parameters. So what is this saying? This is saying that the problem was that m and lambda are not physical parameters, right? So if we keep m and lambda fixed and take capital M to infinity, then you're running into problem. But nobody tells us that as you take capital M to infinity, m and lambda should be kept fixed. Okay? I can take m and lambda also to go to infinity and cancel out the infinities that are coming from capital M. What are we losing? We are losing that we are encountering the fact that the parameters in Lagrangian, m and lambda, they are infinite. But we don't care about if the parameters that we introduce in Lagrangian are infinite, right? As long as the S matrix elements are all finite, we are okay. So we now try to postulate that m and lambda are given by some two new parameters, a and b. Okay, we are trading in equal number of parameters, we are not introducing new parameters. But the relationship between m and lambda and a and b depends on capital M. Okay, capital M is a fake parameter which have to be set to taken to infinity at the end. Okay. So this is what is meant. Instead of m, we think of this as some function of a, b and m and replace lambda by some function of a, b and m. Okay. These will take to be finite parameters. And then we'll try to, we have not said what f1 and f2 are, right? So we'll try to choose our f1 and f2 in such a way that as capital M goes to infinity, this function fa, this goes to infinity, this goes to infinity, as capital M goes to infinity. M of course also goes to infinity. However, this function remains finite as capital M goes to infinity.
F1, F2, do they also go to infinity? Not this.
Yes, f1, f2 will go to infinity. If you keep a and b fixed and take capital M to infinity, see, unless you go to, take this to go to infinity, then you cannot cancel the divergences that was there against anything, right? We are basically cancelling the original divergence that was there because m was going to infinity. Right? If there are some log m term, right, in this, we have to cancel it off by some minus log m term coming from here. So if this can be done, then this means what? This means that we can now think of a and b as our independent parameters. When you write the Lagrangian, it's a function of the fields, and instead of writing m phi square, we will be writing f1 ab m phi square. Okay, where a and b are some parameters. M is some fake parameter that I have introduced in the Lagrangian. Okay, it will also be introduced in the on the momentum curve. And same is true for the lambda phi 4 term. Right? Instead of writing lambda phi 4, I will write f2 ab m times phi 4. We now think of a and b as independent parameters. We are not changing the number of independent parameters. Okay, 2 versus 2. And then the question is, they calculate now an S matrix element fa, okay, which will be given as a function of a and b. Now you take m to infinity. If this function can be made finite, then we are done. Why are you done? Because then this means that when you calculate any S matrix element as a function of a and b, they are finite as m goes to infinity. Now, if you want to do this, you just have to eliminate a and b. Right? Take two S matrix elements which are given as a function of a and b. It's a finite function. Just eliminate a and b, and then you can express third observable in terms of the two other observables. But if these functions are finite to begin with, then this elimination process is not going to give you divergence, any new divergence, right? Because if every observable expresses a function of small a and small b are finite functions, then when we eliminate small a and small b to write a third observable in terms of the two first observables, that will also be a finite function. So if this can be done, then this is guaranteed. Is this clear? The other way is also true. If this can be done, this is guaranteed because you can just take a to be observable capital A and b, the small parameter b to be observable b. Then we have what we have here. So these two are equivalent ways of describing renormalizability of the theory. This has the advantage that we don't have to give any special preference to any particular observables. Then we simply demand that is it possible to postulate some relations that expresses the parameters small m and small lambda as functions of new parameters, but those functions themselves can diverge in the m goes to infinity limit. But what you gain is that divergence can be used to cancel the divergence that was there if you have kept this fixed and taken the capital N goes to infinity. Yes.
Similarly, from the path integral, when we did this perturbation expansion, assuming that lambda was
Small lambda, yes.
Small lambda. So when we trade lambda in and lambda, now we are allowing them to diverge or some function.
We'll see that again. The way we will organize our perturbation expansion is that these divergences will always be higher parts of the coupling constant. Okay? So if there is a relationship from lambda equal to a plus say a square log m, a is, sorry, let's call it b. Okay? So to, at tree level, right, you can make these parameters a and b in such a way that at the tree level, small m is equal to a and lambda is equal to b. Right? Because at tree level there is no divergence anywhere. Right? So this point we can think of this as a perturbation expansion. Okay? Then when we eliminate b in terms of lambda, right, we will write this as b equal to lambda minus lambda square log m. We'll do it in more details later. So it will not be. So the fact that this is divergent, right, it doesn't prevent us from doing a perturbation expansion of this kind. Is this? Okay, so we'll first do the perturbation expansion in the small parameter lambda or the small parameter b, and then to any given order in perturbation theory, we'll see the divergence like that. So it's not that because this is large, we cannot do a perturbation expansion in b. Okay, because the perturbation expansion in b will be done first. Then we will take the capital M goes to infinity at the end.
After is that is after I've done all that is I'm left with a and b. One of these parameters should have small value, right? Because
Yes.
somewhere somehow I've done all
Exactly.
that.
So b will be have small value here.
So that is guaranteed, or that will like one has to take explicit.
No, it is guaranteed because you will always take a b goes to 0 limit first before taking the m goes to infinity. Right? So the perturbation expansion will always be done in terms of b first. Right? So that will be the Renormation program, that the perturbation expansion is done first. Then you worry about taking capital M to infinity. Okay, at the cutoff to infinity. Okay, but this will become clear once I do some examples. Any other questions? So is the basic philosophy clear? What we are going to do? So now I'll focus on first finding a regulator. As I said, this regulator, of course, any regulator in principle could work, but having a cutoff like minus m to m is not a very good way of regularizing the theory. There are better ways, okay, and I'll describe some regularization that will be used. So the regularization that we'll be using is what is called dimensional regularization. Okay, and I'll explain what this means. So let me remind you again that what was the purpose of regularization. The purpose of regularization was to first make the integrals finite. We make the integrals finite, okay, by putting some kind of cutoff, then do our manipulations. And after you have expressed m and lambda in terms of finite parameters, okay, and then At the end, we take the regulator to infinity. Okay, that was the goal. So first, the job of the regulator will be to give finite result for every quantity. Okay, even if it doesn't make sense, okay, physically, so you want a finite result. So this dimensional regulation does that by working in dimensions other than 4. As we saw, the ultraviolet divergences are dimension sensitive. Okay? Lower the dimension, the better the behavior of the integral. Okay? Because it's simply because you are integrating over less number of variables. So in dimensional regulation, what we do is that we work in low dimensions to define the integrals. And then we define the integrals in 4 dimensions by analytic continuation. Now this is a little strange because normally when you talk about analytic continuation, right, you describe it as a function of a continuous variable. Right? If a function, what is the role of analytic, what is the meaning of analytic continuation? If you have a function of a complex variable, an analytic function, if you know the function over any line segment, then you can define it everywhere in the complex plane. Right? That's the meaning of analytic continuation. But when you are talking about dimensions, they are integers. Okay? They are not continuous variables. So if we have an integral, we can define it as some discrete number of dimensions which are lower than 4. Okay, depending on what the integral was to begin with. Say 3, 2 and 1. Possibly 0. But the question is, how do you analytically continue a function if you know its value only at 0, 1, 2 and 3? Okay? So you have to find some tricks, right? And that's what dimensional regulation allows us to do. Right? It turns out that even though actual physical integrals make sense only in integer dimensions, there is a way in which you can define this integral at arbitrary dimension for thinking of dimension as a continuous variable. So we'll see how that is done. So once we understand that, then we'll carry out all our manipulations at this arbitrary continuous dimension. Okay? Formula will make sense, okay, even though they do not make sense physically. We'll carry out this program, okay, by expressing everything in terms of some other parameters a and b. Okay, the m and lambda in terms of a and b. The role of m will be played by d, the dimension of space-time that you are working in. After you have calculated this, okay, and express the physical observables in terms of a and b, then we will take d goes to 4 limit. And we will try to see that in the d goes to 4 limit all divergences cancel. Okay, but the d goes to 4 limit will be taken at the end of the calculation after you have eliminated the original parameters m and lambda in terms of these new parameters here. Okay, if we express in terms of the original parameters, if we work at this level and take d goes to 4, these results will be divergent, right, which is expected because the original results were ultraviolet divergent. Is this clear? So let's see how we can make sense of integrals as a function of dimension. So we'll start with a simple integral because this will basically capture most of what we want to do. ddk over k square plus 2 pi to the d.
So the limit of k will be answered.
Limit of k?
That you get the length.
No, we are not going to put any capital M now. Minus infinity, infinity. Okay, so you are going to make this finite not by putting a cutoff, but by taking d to be small. Okay, so this integral, under what condition is it ultraviolet divergent, convergent?
D is smaller than
How small does d have to be for this to be d minus? D minus? See, let's go to the large k limit, right? Then this goes as r to the d minus 1 dr, right? the numerator. What about the denominator? R to the power 2 alpha, right? This k square R to the power 2 alpha. Dr by R is divergent, right? You have to have this whole thing have a power larger than 1. Okay? So 2 alpha minus d minus 1 should be larger than 1. Right? If it's equal to 1, you still have divergence, right? It has to be larger than 1. So this tells us that d has to be less than 2 alpha, right? If d is less than 2 alpha, then you are okay. Okay, so this integral can be defined for d less than 2 alpha. Is this clear? So how do we do this integral? So let's assume that this is equivalent. Okay, this you can always assume because you can always make the Lewis rotation and perform the integral in the equivalent space. Then this integral can be written as integral 0 to infinity r to the power d minus 1 dr omega t minus 1. This is the volume integral r to the d minus 1 dr because this is a d-dimensional integral. Omega d minus 1, why? Because it's a d minus 1 dimensional sphere, right? If you have a d-dimensional integral, you put it as a radial integral and d minus 1 dimensional unit sphere. So this is the volume of d minus 1 dimensional unit sphere. Divided by r square plus c to the power alpha. Create two particles. First, let's get rid of this c. So you can define r as square root of c times rho. Okay, I just want to get rid of the c from there. Then the c dependence comes at a c to the power d. Okay, because c to the power d by 2 minus alpha. Then you have omega d minus 1 over 2 pi to the d. I just rewrote this integral in a row variable so that the c dependence just factors out. Okay, because if I write rho r equal to root c times rho, then this becomes a c to the alpha comes out, and you have a rho square plus 1 to the power alpha in the denominator, and then from the numerator you have a c to the power d minus square root of c to the power d minus 1 and the square root of c. So that gives you total c to the power dy. Okay. Now this integral is divergent if d is larger than 2 alpha. Okay, which is expected because if d is larger than 2 alpha, then this grows too fast and infinite, right? And you get the original convergence. But for d less than 2 alpha, this integral, see now, the way I have written, this can be made sense of even if d is fractional. Here there is no problem, right? Even if d is fractional, you can make sense of this. So you can calculate this for any d, even fractional d or irrational d, any real d, as long as d is less than 2 alpha. And the answer for this I'll write down. This you can try to check. This is gamma alpha minus d by 2 divided by gamma 1 plus 1. Okay, if d goes to 2 alpha, then this goes to gamma 0. Okay? Then gamma has a pole at 0. Okay, so you get back the divergence. Okay, but otherwise this is a function. Omega d minus 1. If you think of this as a volume of a d minus 1 dimensional sphere, then of course it can be only defined for integral d. Volume of a d minus 1 dimensional sphere doesn't make sense for fractional real d, arbitrary real number d. But what one can show is that it is possible to rewrite this in a way that can be made sense of an arbitrary d. Okay, just like we made sense of this for arbitrary d, it is possible to rewrite this as an integral where d appears in the integral, okay, not in the form of integrating over d minus 1 variables. So if you think of it this way, you have to integrate over d minus 1 variables, right? But it is possible to convert this to a form in which we don't think of this as an integration over d minus 1 variables. D just appears in the as an argument in the integral. With that, I'll write down the formula. Okay, maybe I'll give this as a homework problem to do this. That this one has a formula which is 2 pi to the power d by 2 over gamma of d by 2. Here I made a mistake. There is a gamma of d by 2 here. So the full formula. Okay, the formula for this has a gamma of d by 2, and I think there is also a 2. Okay, so this integral gives you this. Anyway, this is a standard integral, right? So you can try to do this, or you can try to put it in Mathematica and see if Mathematica can give you the result. This we should find that this is the result you get from this. So this, as I said, it is possible to rewrite it in a way where it's an integral with d as a argument of a function, and this is the result that you get. Okay. So let's at least check that this has the right value for known cases, right? So d equal to 1, what we expect for d equal to 1, omega 0. 0 dimensional sphere. 1. So let's see what we get. 2 times d equal to 1, right? Root pi divided by gamma of half. Gamma of half is how much? Root pi. Gamma of half is root pi. So why is it 2 and not 1?
Minus 1 to 1.
0 dimensional sphere. So how are you defining 0 dimensional sphere? X square equal to 1, right? In n dimensional sphere, right, has x1 square plus x2 square up to xn plus 1 square equal to 1, right? So 0 dimensional sphere should be x1 square equal to 1. x1 square equal to 1 has two solutions, right? Plus minus 1. So a unit sphere, in a 0 dimensional unit sphere actually has 2 points, okay, not 1 point, that's why it's 2. So let's look at d equal to 2. So this is for d equal to 1, right? D equal to 1. So d equal to 2, you get 2 times pi divided by gamma of 1. Gamma of 1 is how much? Gamma of 1 is 1. So this is 2 pi. This is the correct result for one dimensional circle, right? So for d equal to 3, we get 2 pi to the power 3 by 2 and then gamma of 3 by 2. How much is gamma of 3 by 2? Half gamma half, right? So half times root pi. So this is half times root pi. Right? So that gives you 4 pi. Right? Which is the correct results for a 2-dimensional sphere. D equal to 3 means the corresponding sphere will be omega 2, right? A 2-dimensional sphere has area 4 pi. You can check that for d equal to 4 you get by a 2 pi square that we had said earlier. Anyway, so, but now we are in business, right? Because now we see that everything that we have here is written as an analytic function of d. So now we can think of d as a continuous variable. And then eventually recover the result by taking d goes to 4, but that has to be done only at the end of all this renormalization procedure. Right? If you try to take d goes to 4 in the middle of the calculation, you will find the results are divergent. You have to first adjust your parameters, okay? Eliminate the m and lambda in terms of these new parameters a and b, okay? And only at the end, keeping a and b fixed, you have to take d goes to 4. Is this quite clear? So let me correct on everything and write this. So you get integral dv over 2 pi to d 1 over d square alpha as c to the power 2 by 2 minus alpha, then 2 pi to the d by 2 over gamma by 2. If this came from the omega d, then you have 1 over 2 pi to the d. Okay, that's this one. And then this factor over here, gamma of d by 2. So this cancels, gamma d by 2, this 2 cancels this 2. So this one I can write as 1 over 4 basically this 2 to the power d I wrote as 4 to the power d by 2, and this pi to the d and pi to the d by 2 got cancelled and become pi to the d by 2. Okay, so 4 pi to the d by 2 and then gamma alpha minus d by 2. Is this clear? Now, since part of this manipulation was formal, right? For example, this made sense only for certain range of alpha, right? Or certain range of d. This, for example, I just replace it by this. There are various consistency checks you can try to carry out. Okay? For example, exercise. Check that del del C of both sides. What do you mean by this? If we take del del C of this side, what will you get? You will get c d by 2 minus alpha, c to the power d by 2 minus alpha minus 1, right? This is just a constant. On this side, if you take del c, this will become minus alpha times k square plus c to the power alpha plus 1, right? That integral can be again evaluated by the same formula, right? With alpha replaced by alpha plus 1. So you should be able to check that whatever you get by directly differentiating this agrees with what you get by differentiating this and evaluating by this formula again. So in dimensional regularization, once you have used the dimensional regularization, you can carry out the usual manipulations of differentiations, okay, taking it from outside to inside, okay, as you can see from this formula. We may have integrals of the following form: d4k over 2 pi to the t, sorry, ddk over 2 pi to the t. How do we evaluate this? The point is that for evaluating this, you don't have to go back again and do the integral all over. Okay, from whatever formula I have given here, you can actually calculate this. So the trick is that you first see that this integral just by Lorentz invariance, and in this case rotational invariance because you are in the Euclidean space. In the Euclidean space, by rotational invariance, this is proportional to what?
Theta mu.
After you do the integral, k integral, right? Yes, this is proportional to
Theta mu.
eta mu nu or delta mu nu in this case, right? Because we are using Euclidean. Okay, let's say eta mu. Doesn't matter. So eta is delta for Euclidean. Eta is delta for Euclidean. So it should be some constant a times eta mu, right? Now you can calculate a by simply multiplying, taking the k with eta mu, both sides. So if you take the k with eta mu, what is the left hand side? Eta mu times. What is the left hand side? What is the right hand side? Yes? It's d times a. Right? Don't use 4 because we have used dimensional regularization. So this is the thing you have to be careful about. Okay? That once you are working in d dimensions, right, you should never think about 4. Right? Always think in terms of d dimensions. We'll see that this is not always possible. Okay, and that's where we have some serious trouble. Okay, but right now at least we are okay. Okay, so eta mu nu is d. So d times a. So d times a is integral ddk over 2 pi to the d 1 over k square plus c to the power alpha. So what do you get here? Eta mu nu k nu. That is k square, right? No d over there. So this is k square, but I can write this as k square plus c minus c. So this is integral ddk over 2 pi to the d 1 over k square plus c to the power alpha minus 1 minus c. Sorry, minus c over k square plus c. Okay, I just cancelled one part of k square plus c from the first term. The second term was just minus c over k square plus c. And now the idea is that both of these integrals are all of this form. Right? In the first one, you just replace alpha by alpha minus 1. Right? And the second one, you just multiply by minus c. Okay, so you don't have to do a new integral. Right? This formula is enough to evaluate that. Let me give you a few more details and then I'll stop today. So we can ask how to deal with multiple denominators, right? Because this is too simple an integral. Because typical integral, so let's write multiple denominators. So typically you have an integral of the following form: ddk over 2 pi to dt. And then 1 over, say, e1 plus a plus b1 square plus m1 square. And this is a typical term that we have. And in one loop, we have multiple denominators. So the question is, how do we deal with these? Okay, so far we have been talking about only one denominator, right? So what we do here is that we use this formula that if you have 1 over a1, a2 up to n, okay, this is what is called the Feynman parameterization. There is general formula, this is n minus 1 factorial integral 0 to 1 dx1 integral 0 to 1 dxn. There is a delta function. Okay, this is an identity. If you have multiple integrals, then you can show that this is true. This is identity. Okay, you can try to check this in simple cases. Take a1, a2. Right? In this case, you have two integrals, dx1, dx2, but because of this delta function, right, there is really only one integral, right? Integral dx1, x2 has to be set equal to 1 minus x1. And then you have a1 x1 plus a2 times x2, but x2 is 1 minus x1. Okay? So now you can do this integral explicitly and you can check that this should be 1 over a1. Okay? And this way you can try to verify this for arbitrary cases. So using this identity, what we can do is that we can combine all these denominators together, okay, by into a single denominator, what is a higher power. So then this integral will write as integral dx1 I'm ignoring the I epsilon right now. this. Here's what we are doing. First of all, I forgot to mention here this P1, P2 up to Pn, these are some combinations of external momentum. Okay, that's the way you should think of this. So what I am doing is that I am thinking of this as A1, A2 up to N in the denominator, and using this, I write it as x1 times A1 plus x2 times A2 up to xn times n to the power n. Okay, this integral over x being taken. Is this okay? But now we just have to simplify this. So in the denominator we have a square times x1 plus xn. The x1 k square multiplies all of them, right? K square multiplies x1, x2 up to xn. But this is of course just 1 by this delta function. This is 1. Then we have k dot plus 2 k dot sum over I equal to 1 to n xi 2. That is by multiplying, expanding up 2k dot p1, 2k dot p2, 2p dot p1. And then you have the rest. So sum over I equal to 1 to n xi times pi square plus n square. Okay, I'm forgetting about I epsilon right now, we can put it back at the end. Okay? But now we can just complete the square. Okay, so I can write this as k plus sum over I equal to 1 to n. I equal to 1 to n xi pi square. That takes care of this, and you have to subtract off minus sum I equal to 1 to n xi square pi square plus sum I equal to 1 to n xi pi square semi square.
So the I epsilons are
I epsilons are all with mi. I mean I epsilons you can always put because with mi you can put an I epsilon, right? Mi square minus I epsilon. So this raised to the power n. But once you are doing Euclidean, you don't really need the I epsilon. Right? I epsilon is needed when you do the Lorentzian integral. Right? Then you have to keep track of other poles. Okay, but now we are done, right? Because this you define as some new variable k prime. And this you call C. So using this we can write this integral as integral 0 to 1 dx1 0 to 1 xn delta this because this whole thing we are calling C. This of course is a function of the x size. And on this now we apply the formula. Okay, so this is the way we deal with multiple denominators in dimensional regularization, right? Or to try to evaluate an amplitude which has multiple denominators. Most of the amplitudes are of that kind, right? Like the one that we did here. These are two denominators, right? So for this n equal to 2, we have to combine it this way to get the
Sir, wouldn't that be we can see
Yes.
the summation xi square plus wouldn't that be summation xi plus
summation.
we can see.
Yeah. This is okay or no?
I'm saying wouldn't that be the whole square instead of xi square plus sum xi gain tables.
This is sum over xi pi square, no? Because x1 times p1 square plus m1
The
square.
first term we see.
First term should be, oh yeah, thank you. This should be sum over xi pi whole square, yes. Because you complete the square, right? And sum over xi pi whole square has to be subtracted. Okay, so once we have this, okay, we substitute the expression for C, we will evaluate it using dimensional regularization, and then we carry out the x integrals. Okay, often you don't even have to do the x integrals. Okay, to extract a finite piece, okay, we can just work at this level. So maybe I'll stop here. Next time we'll discuss a few more generalizations, because this, for example, is at a level of one loop. Right? We have dealt with multiple denominators but only one momentum integral. Typically, we will have multiple momentum integrals. If you have k loops, for example, there will be k momentum integrals, right? So how do we deal with those cases? Okay, in dimensional regularization. And then we'll also have to discuss what to do with the gamma matrices. Right? Because we have now generalized also the gamma matrix algebra in arbitrary dimension. Right? So there will be d gamma matrices, and d in general is not an integer. Right? So you should see what to do with those.